Today I'm going to talk to you about Taylor polynomials. Taylor polynomials are a specific type of power series. So the idea that Taylor had was with some of these functions that were a little more complicated, some of the transcendental functions, he had difficulty dealing with in terms of specifically integration. For example, the integral of sine of x squared. There's no elementary antiderivative for that one. So it makes it difficult sometimes to do some of the calculus. So he thought, well, maybe I could come up with a polynomial that pretty closely matches the given function that I'm trying to deal with. So for example, let's look at the sine of x graph. Let's say we wanted to come up with a function that matched the sine of x graph around, let's say, at x equals 0. So we have to pick some part of our graph that we want to match with a polynomial. Well, the simplest function to use would be a constant function. And so if we just used y equals 0, because the sine of 0 is 0, we know that that constant function would match the sine graph at 0. But it doesn't match it very well anywhere else, except for maybe the other x-intercepts. So maybe instead of a constant function, maybe a linear function would be better. And so we would like this linear function to match the sine graph at 0. But maybe we would like the slope of this line to match the sine's derivative at 0. And so by doing that, we see that not only does it match the sine function at 0, but closely around 0 it also matches. But Taylor wasn't happy with that, so he said, well, what about a quadratic? Or maybe a cubic? Or what if I keep going? And so he started trying to match higher order polynomials to a given function by calculating more and more derivatives of that function at that particular value and trying to make the concavity match, etc. And so as you can see, as my degrees go up and up, that the polynomial matches the sine graph further and further away from 0, which was where we chose to center it. Now it doesn't have to be centered at 0. It could be centered anywhere, but 0 seemed to be a good number to start with for centering. So a Taylor polynomial approximates a given function centered around a certain value for x, we'll call it c for centered, is going to be given by this formula. And so what he did was he just started matching derivatives with each higher order polynomial. So an nth degree polynomial that matches a given function or approximates a given function just simply goes up to the nth power for x. And as you can see in the last term, your x will be to the nth power, and we're using the nth derivative of our function evaluated at that c value. In the case of my example, it was at 0. Now there was another guy named Maclaurin who just wanted to focus on functions that matched around 0. So all the Maclaurin polynomials are a subset of the Taylor polynomials. So Maclaurin just focused on centering all of his polynomials around 0. Taylor, on the other hand, didn't just exclusively use x equals 0 for where he was centering them at. So this is the nth degree Taylor polynomial, and that's how we're going to calculate it. If I condense it down to sigma notation, it works out very nicely because there's a nice pattern there. So we're always evaluating a certain derivative at wherever we're centered, dividing by the factorial of that derivative, and then we're raising x minus c to that same power as well. So the kth derivative of f at c divided by k factorial times the quantity x minus c to the kth power. And we're adding up all these terms, so we're coming up with a polynomial of nth degree. Now it's important to understand that this is only going to approximate our function. On the other hand, if we kept going, instead of stopping at n, we keep going to infinity, then this infinite polynomial is actually going to equal the function. And so it's important to understand that an nth degree Taylor approximates a function, whereas the infinite polynomial will actually equal the function. So let's look at an example. Let's try and find a fifth degree Taylor for the function e to the x, and let's center it around 0. So the first thing you always need to do is start calculating derivatives up to that degree. Now e to the x is going to be very simple because it's its own derivative. So I start with my function, and I'm going to evaluate it at 0. And then I'm going to calculate the first derivative. And I'm going to evaluate that at 0. And then I'm going to calculate the second derivative and evaluate that at 0. So in each case, I'm calculating the next derivative, and I'm going to evaluate that at the particular x value that we're centered at. In this case, at x equals 0. Once you get to the third derivative, we stop using tick marks, and we put the number in parentheses. So the third derivative at 0. Okay, so now I have all the values I need to come up with my fifth degree Taylor. So once again, I'm using this formula, and I'm going to start plugging in all the values that I just calculated. So my function is f of x, which is e to the x, and that's going to be approximately equal to my fifth degree Taylor polynomial, which is going to be f of 0, which is 1, over 0 factorial, times x minus 0 to the 0 power. I tend to write this all out because it's easier to see the pattern. Then it'll be the first derivative evaluated at 0, divided by 1 factorial, times x minus wherever we're centered to the first. And then the second derivative evaluated at c, at 0 in this case, over 2 factorial, times x minus 0 squared. I don't need to keep writing the parentheses, so I'll just write x squared. Plus the third derivative evaluated at 0 over 3 factorial, x to the third. Plus the fourth derivative evaluated at 0 over 4 factorial, x to the fourth. And finally the fifth derivative evaluated at 0 over 5 factorial times x to the fifth. And so now we have our fifth degree Taylor polynomial, which approximates e to the x, and it actually equals e to the x at x equals 0, because that's where we centered it at. And as you pull away from 0, it should match it pretty well for a while. How well does it match it? Well, more on that later. So this is our fifth degree Taylor polynomial that approximates e to the x around x equals 0. Now you can leave the factorials in the bottom. Sometimes you'll see them actually worked out, so it'll be over 2, over 6, over 24, over 120. But I don't think it really matters. I think it's nicer to leave it with the factorials because you see the pattern. Now one thing we can do is we can use this fifth degree Taylor polynomial to estimate what would f of 0.2 be. So in other words, what's e to the 0.2? So with the polynomial, if I plug in 0.2 for every x, and then simplify, I get 1.2214. And you can see when I actually punched in on the calculator e to the 0.2, I got 1.221402758. So this fifth degree Taylor approximated, or actually matched, the function at 0.2 to 4 decimal places. And that was only a fifth degree polynomial. So if we went to a higher degree, 6, 7, 10, 20, it would match the actual function's value at the given, in this case, 0.2, even further. Now there's a few functions that you should be familiar with for the Taylor polynomials. So e to the x, which we just did, centered at 0. Another one is the natural log of x. We can't center that at 0 because it's not defined at 0. So that's usually centered around 1. Although you will see in some books, they'll change it and it'll be the natural log of 1 plus x, centered at around 0. And then the sine of x and the cosine of x, and 1 over 1 minus x. And sometimes even f of x equals arctan of x, you'll see as well. In the IB formula booklet, they have, I think, 4 of these 5, and they also have the arctan. So what do these Taylors look like? Well, if you work them out, like I just did for e to the x, there's your e to the x. The natural log of x centered around 1, so notice it's x minus 1 in all the parentheses. E to the x was centered around 0, so it's x minus 0, so we don't need to use parentheses for that. The sine of x, notice for sine of x, it's all the odd powers of x, and we have alternating signs. And if you think a little bit about what it would take to create the Taylor for that, and started doing derivatives of sine, you see how it jumps between sine and cosine, and negatives and positives. And at certain values, the sine of 0 or negative sine of 0 is 0. So that's why some of the terms, every other term is going to be left out because we get a value of 0 when we evaluate it. And also notice the powers of x, the denominator is that same number factorial. For the cosine of x, it makes sense that that should just be alternating terms of the even powers. You can think of 1 as x to the 0. Also, the signs are alternating. And instead of working out the Taylor for that, you simply could just take the derivative of this. The derivative of x is 1. The derivative of negative x cubed over 3 factorial is negative x squared over 2 factorial, etc., etc. And vice versa. If you differentiated the cosine and then took the opposite of that answer, you would get your sine Taylor polynomial. And finally, that 1 over 1 minus x, which is probably the easiest to remember. And you might also notice that it looks like it's a geometric series. And for that geometric series, r would be equal to x. And on the left side, the fraction, then you might recognize that as the formula for the sum of an infinite geometric series, which is 1 over 1 minus r. And in this case, r is equal to x. You could also come up with this Taylor if you had done long division on the 1 minus x divided into 1 and continued that on forever. You would get your 1x, x squared, x cubed, etc. So that's the basics for Taylor's polynomial. Next we'll do some of the interesting applications so we can come up with Taylor polynomials for a lot of other functions.